Hi, everyone. We're going to go ahead and do the background lecture for activity 30 about simple circuits. So let's jump in. Grab your note sheet. So in order to have a circuit, you need something to push charge around in the circuit. And in many circuits, this is accomplished by something called a cell. So a cell is simply something that organizes charge. The cell organizes charge, and it's an energy conversion. It's converting chemical energy from a chemical reaction to electric potential energy, which then can be used to do work. So how does this happen? Well, one way that this could happen is by taking two different kinds of metal and putting them in some kind of an acid or an electrolytic solution. Now, I'm no chemist, so we'll just give you the basics here. One possibility is you take a piece of zinc and a piece of copper, and you put them in the acid, and the acid will attack the zinc. And one thing that it can do, this is like sulfuric or hydrochloric acid, might eat some zinc ions off, and what in this case maybe zinc +2, which means essentially what the zinc is doing is it's leaving a couple of electrons behind. And so this chemical reaction, as it eats the zinc ions off, leaves the zinc rod negatively charged. So we end up with a net negative charge to the zinc as electrons get left behind. In the copper reacts differently and at a different rate. And so we also end up with some ions being eaten off the copper, but not to the same degree. And so it's this disproportionality, the fact that one of them is more negative than the other, that creates, in this case, a higher potential. And whichever side is less negative becomes the positive terminal of our battery. So we end up with one that has a higher potential. We can label that as the positive terminal, and one with a negative terminal with the lower potential. Once we have this, we can hook a circuit. We can hook a conducting path up to it, and charge will flow between the two. The schematic symbol for a cell looks like a short line and a long line representing the low and the high potential side of the battery. You can remember that based on the long line is higher, so we have a higher potential. Short line represents the lower potential side. So this may be the zinc, and this may be the piece of copper. Now, sometimes we use the word somewhat interchangeably. Like if you go to buy one of these at the grocery store, you might buy a D cell battery or a AA cell battery. You're looking at a single cell. When we use the word battery, a battery is technically a collection of these cells is called a battery. Because you can place them together and add them up to create higher voltages. So the schematic symbol for a battery looks like multiple ones put together. So this is for the battery, and this is for the cell. So you even do this if you put batteries in a flashlight or a AA. Say AA's are 1.5 volts. If you put two AA's in a flashlight, you get 3 volts. Have a combined effect. Car batteries, for instance, consist of, I believe, six 2-volt cells. So you get a total of 12 volts for a car battery. Another symbol that we'll come across sometimes when we're talking about batteries and what's happening inside of them, or cells and what's happening inside of them, is something called EMF. Symbol for EMF is this kind of scripty looking E, this curly looking E, and it's a historical term. It stands literally for electromotive force. And before circuits were really well understood, the thought was that batteries were like pushing charge, like a force pushing them. It's not actually a force. It's related to energy. So I'm not going to write that definition because it's a historical mistake. The EMF, or the electromotive force, is defined to be the energy, my word here, the energy converted from chemical to electric per unit charge. Energy per unit charge. And so energy per charge would be a joule per coulomb, which is by definition a volt. So the EMF is essentially, it's the voltage being produced by the cell. The rate that it's creating, or not the rate, but the total amount of energy per charge that's being created due to the battery. Now, we have to distinguish between EMF and something called the potential difference. And Sometimes this is just abbreviated PD. Potential difference, it's also a voltage. But a potential difference is defined to be the energy converted from electrical to thermal energy per unit charge. And so it's also an energy per, so joule per coulomb. It's also measured in volts. So both of them are measured in volts. But you can kind of think about the EMF as the source of energy, the chemical reaction, and then the potential difference as being the use of that energy, being used to create heat in a resistor or something like that. So for instance, when we distinguish between the two, if you think about a chemical cell, we could draw our symbol here for our long and short line. But the cell itself, when you hook this cell up to a circuit and charge starts flowing through it, the charge has to flow through the zinc and through the copper, and they have resistances. So there's some resistance to the cell itself. So if this, kind of draw a dotted line right here. If you go to the grocery store and you buy yourself a AA battery, this is your AA battery. It's basically something that's converting chemical energy to electric, but it's also something that's wasting some energy because it has to push charge through itself. So there's what's called an internal resistance. So we'll use little r for that as our EMF symbol here. And little r is called the internal resistance. And if you had a perfect cell, there wouldn't be any of that internal resistance, because internal resistance is wasted energy. Its heat's going to be lost, energy is going to be dissipated in the battery itself. So when you hook your AA up to something else that maybe you want to use, maybe you're going to try to heat something. So you got a heating element. You have your resistance of that heating element. Oftentimes we call this the load. It's what the battery is trying to do work on. Okay. And so this seat of EMF, sometimes we use the word seat of EMF to talk about our EMF. It's going to send current, and current's going to flow from the high potential positive side to the low potential negative side, since we treat it as the flow of positive charge. So there's going to be a flow of current. That current's going to flow out of the cell. It's going to flow through the load, and it's going to dissipate some energy in the form of heat. But then it's going to flow through the cell itself, and there's going to be some dissipated heat inside the cell. Okay. So we can distinguish between what's happening inside the cell as the chemical energy per charge, but then the potential difference is what's happening outside of the cell. And the idea is that if it was a perfect cell, they would be the same. If there was no internal resistance, then whatever volts you have here are all going to be used in the load. But oftentimes in real life, these things are going to be different, because you've got voltage, potential energy being produced in the cell, but some of it's getting wasted here. And then what you get out as your potential difference ends up being less than the EMF could supply, because you're losing energy inside the cell. So we can write this in the form of an equation. Basically, it's an energy conservation expression. We could say that the EMF, which is the available energy in that cell, is getting used up to do two things. We know that multiplying a current times the resistance gives me a voltage. So we're going to have some of the volts of the EMF being used inside the cell itself. So current, this is the same I flowing everywhere, whatever that current is, times the internal resistance. And then there's going to be the current times the load's resistance. So in other words, if this is 9 volts, maybe the EMF is 9 volts, and then maybe 3 of those volts get used up inside the battery, then only 6 volts are available for the load. So this is an expression of energy conservation. If we're looking at this, at what's happening here, we're essentially looking at the left side of the equation, and we're thinking, okay, chemical energy is getting converted into electrical energy. That's what's happening here with the EMF. So that's the EMF side of the equation. And that has to be equal to what's happening over here on the right side of the equation, where electrical energy via the current is getting converted into thermal energy into the resistors. And it has to be the same energy. It has to be accounted for in both places. That's where the potential difference is happening over here. Okay. On the IB data sheet, they basically give us this equation on the IB data sheet, but they just factor out the I. So we can write it more simply as the EMF is equal to the total current times the load resistance plus the internal resistance. So this is the way it's given on the data sheet. And we'll see an example a little later of how to use this equation. Another thing that sometimes shows up on the IB test when it comes to using cells is just recognizing that this chemical reaction, like all chemical reactions, can't continue forever. Basically, you're going to have charge being drained out of this, and then the chemical reaction is going to kick back in, start eating away at that zinc and that copper. Eventually, the chemical reaction can't continue anymore, and the cell basically becomes a dead battery. So if we looked at the available EMF, the energy per charge you can get from the battery, as a function of time. Let's say we're going to run that battery for a while. We'll leave your flashlight on for a long period of time. Generally, what a cell will do is it will keep providing that EMF. The chemical reaction keeps happening. It just keeps giving you the energy per charge. And then at some point, it starts to decay, and the chemical reaction can't quite keep up, and then it kind of tails off. And so kind of recognizing that point where it's starting to drop, you might consider this point to basically be the end of its useful life. And for most cells, you just throw them away and you get a new one. Sometimes batteries or cells are rechargeable, meaning the chemical reaction is reversible. And if you hook them up to another source of voltage that's pushing charge the other way, you can get the chemical reaction to kind of rewind itself. And you can run the battery through a number of cycles, or the cell through a number of cycles. Go ahead and flip our page over. Look at the big picture here. This is a short lecture. It's the last page of it. We're looking at energy conservation when we understand maybe how a cell works in terms of an entire circuit. So let's assume we've got some source of EMF, which is where the energy is being produced. You can think about this as essentially what it's doing is it's separating positive and negative charge, like lifting it. Negative and positive charge want to come together. It's analogous to like lifting a bowling ball up where it doesn't want to be. And so it looks like that a little bit. When you think about the way that current flows in the circuit away from the high to the low side, you're going to have a flow of current in the clockwise direction around the circuit. So we'll draw some arrows here to represent our current flowing through the circuit. And in this case, what we're seeing is like this charge is getting pushed around. Then we get to the cell itself. The chemical reaction is lifting that positive charge up to the high potential, and then in which case it kind of falls down again. So you can think about this seed of EMF. We could say that it lifts charge, moves that positive charge where it doesn't want to be to the high potential, in which case it can fall. So it's a little bit like a water pump, lifting water uphill, and the water flows back downhill to the low side again. So then as it goes through each of the resistors, we get charge flowing through each of our resistors. Say we've got resistor 1, 2, and 3. Each one representing some load, and each time the current flows through the resistor, some energy is dissipated. Some of the volts are used because we get V equals IR. We could think about that as, we could say, charge falls. And it drops down and it releases its energy, just like dropping a bowling ball would release its energy. So this would be analogous to like a water pump, and then maybe you got like a series of waterfalls in your backyard, and it goes down one waterfall and the next one and the next one from one pond to the next, and then the pump lifts it back up again. Would be a helpful way of thinking about this. Okay, so this is the energy coming in and this is the energy going out, and we're talking about energy conservation. So essentially what we're saying is that the volts, the energy, the joules per coulomb that we put in have to be accounted for in the energy going out. So we could say that that EMF is equal to IR1 plus IR2 plus IR3, which is the potential given to each of my 3 resistors. It has to be accounted for. So if we think about this, here's with 3 loads, but we think about this in the case of maybe just hooking a battery. So this looks, again, I'm using the terms interchangeably, battery and cell. Maybe it physically looks something like this, and you know that the little nub here is the positive end and this is the negative end. So that means what's happening inside of this thing is that there's a chemical reaction. We can represent that here, and notice I drew the long line on the left to correspond to the positive side and the short line on the right. But the cell has some internal resistance, and again, that's not avoidable in real life. So we got the EMF, we got our internal resistance, something like this. Okay. And if you tried to measure how many volts, if you hooked a voltmeter up across this thing, what you would be doing is measuring something called its terminal voltage, or its terminal potential difference. So between these 2 points, there's going to be a difference here. We'll call this as our terminal potential difference. And that terminal potential difference from one end to the next, like if you look at the side of the cell, it might say 1.5 volts, and you hook it up to a voltmeter, and it gives you 1.5 volts. That's the EMF of your source. But that's only if no current is flowing. So the problem becomes, like, if it's not hooked up to anything, it's going to read the right, the terminal potential, and the EMF will be the same. So maybe this is 1.5 volts, and your terminal potential is 1.5 volts. But as soon as you hook that AA battery up to a load and you create a circuit, then current's going to start flowing. And as the current starts to flow in that cell, it's going to flow around like this. And what's going to happen is some of that 1.5 volts is going to get used up in this internal resistor. Okay? So let's say you lose a 0.5 volt, and maybe your terminal potential that the load is getting is only 1 volt. And you're thinking, wait, I bought a 1.5 volt battery. Why am I only getting 1 volt out for my resistor? It's because you're losing some of the EMF inside the battery. And you don't when there's no current flowing, but as soon as current flows, that heat starts happening. And if you can feel a battery when it's run for a while, it does begin to get hot. So your terminal potential difference is going to always be equal to whatever your EMF is minus whatever voltage is getting used up in the internal resistance. Okay, so if no current's flowing, then they're the same, but the more current flows, the less you actually get out of the battery, the more you end up wasting inside the cell. Okay, so again, kind of big picture wise, this term right here, this EMF, that's your chemical to electric per coulomb. And over here, we have our thermal per coulomb dissipated in the internal resistance. And effectively what that means is that the battery gets hot. That energy has to go someplace as it heats up. Okay, so that ends the material. Let's take a look at a few example problems of how we would use this idea of internal resistance and EMF in solving a couple of simple problems. So before we do so, let me just point out what we have on the data sheet to help us. We've got some different symbols that we'll see in our circuits. So the cell and the battery. We'll talk more about switches and AC a little bit later. We've seen the voltmeter and ammeter already, the resistor. We might see this symbol here, an arrow like this is a variable resistor. So there's usually some kind of a knob or a slide on the side of that resistor where you can change it and you can get different resistances out of the resistor. Equation-wise, we just have this expression, which is our EMF, the current, and then this is the load, and then the internal resistor. So here we go. Number one. The first question says, calculate, or a cell of EMF 6 volts and internal resistance of 2.5 volts is connected to a 7.5 volt resistor. So what I almost always would encourage you to do if you have the time is make a sketch of this just so we can visualize what's happening. Okay. So we have the EMF, the little EMF symbol here is 6 volts. And then we have our internal resistance. And it doesn't really matter whether I put it to the left or to the right of this cell. It's just in line with it. It's in series with it. So little r is going to be 2.5 ohms. Okay. So that this would represent what I would actually have. This would be my cell, okay, with its internal resistance. You don't have to draw the square around it, but that could be helpful. And then we have our load on the outside looking like this, and that's 7.5 ohms. Okay. So there's going to be some current flowing, and that current's going to be flowing around like this from the high to the low side, and that's the first question. I have to figure out what that current is. So in general, current is whatever voltage I have available. In this case, the EMF divided by resistance. So I equals V over R. So the question is, I've got 6 volts available. How much resistance does that 6 volts see? And it sees the 2.5 ohms, and it also sees the 7.5. So it's the combined resistance of everything that it sees. 2.5 and 7.5 add up to 10. So it sees 10 total ohms of resistance. So the current that's flowing is 0.6 amperes. And that flows through everything. It flows through the cell. It also flows through the load. What's the terminal potential difference across the cell? How much is the load actually going to see? So once we get outside of the cell. So what I have to do is I have to think, okay, I've got my terminal potential difference. that's going to be whatever the EMF is minus whatever is lost inside the cell. Okay, so I know I've got 6 volts, and if there's no current, that's what I'll see on the outside of the battery, but then I've got my 0.6 amperes flowing through 2.5 ohm resistance, internal resistance. There's going to be some loss there. So 0.6 times 2.5 is 1.5 volts. So I basically I'm losing 1.5 of my volts inside the battery itself. So therefore, what's available for the load is only 4.5 volts outside. So ideally in real life, your internal resistance is really tiny compared to your load. But when they're similar like this, then you end up really splitting that voltage up and not having a lot to use outside. The final question asks me how much energy is lost. And so it's not lost in the sense of destroyed. It just means basically heats up the battery in the cell when charge flows for 10 seconds. Okay. So I'm going to use 2 equations for this. One, these are formulas we learned before. I first got to figure out how much charge flows through. And I could use my current equation to do that. Current is just charge per time. So that's where the 10 seconds is going to come in. And we know the current flowing is 0.6 amperes. We need to see how much charge that represents. It flows for 10 seconds. So 10 times 0.6, that means the total amount of charge flowing through this circuit is going to be 6 coulombs of charge. And that 6 coulombs of charge, it moves through everything. It moves through the chemical reaction in the EMF. It moves through the internal resistance. It moves through the load. Now, I don't care about the place where it's being wasted. That's wasted energy is inside the load. It's the internal resistance. So I need to look particularly in little r. And in little r, what I can do here now is I can use this expression that V equals W over Q. So this is the relationship between voltage, work, and charge. And we already figured out how many volts were being lost inside the battery. It was 1.5 volts being used inside the internal resistance. So that's what I'm going to put for V. And that's comes from 6 coulombs moving through. So I could figure out how much work is being done or heat is being created in the battery. 6 times 1.5, that gives me work of 9 joules. So 9 joules of heat being created over the course of 10 seconds inside the battery itself. Okay, flip your page over. We're almost done. Final question. We get to draw our variable resistor circuit here. A battery is connected in series with an ammeter and a variable resistor R. Again, let's draw that thing. Okay, so we'll draw our battery, which is our EMF. And I got to find that. I don't know what that is. This is going to have, we're told that there's some internal resistance, and I don't know what that is either. I got to find that. They're both unknowns. Okay. And then it's in series with an ammeter. So we'll put an ammeter, and it doesn't matter. I could put the ammeter here, or I could put it over here. It's just in a row with it. It doesn't matter where I place that. And then we'll have our resistor, and this resistor is variable. So we'll draw that line through it. That means you can just change it to different values. Okay, and here's my circuit. Okay. So again, what's in the dotted lines here is the physical object, my AA, my AAA, whatever that is. It has some internal resistance. Okay. So here's where we can use our equation on the data sheet. The total EMF, or energy available, gets divided up in the internal resistance and the loads. That's going to be equal to I times the quantity, the resistance of the load plus the resistance of internal. And I'm going to apply that with these numbers here. So I'm given some values. When the load is 6 ohms, the ammeter, the current flowing is 1 amp. We could write an equation with that. We could say the EMF is equal to 1 ampere when R is 6 ohms. So here I have a formula that has 2 unknowns. I don't know my EMF or my internal resistance. Okay. So I need another equation. Well, I also know that when the resistance is 3 ohms, the current is 1.5 amps. Okay, so when we change the load to 3 ohms. So I can write it again. EMF, I get 1.5 amperes when the load is 3 ohms plus R. So I basically have 2 equations that have the same 2 unknowns, the EMF and the internal resistance. I just need to solve this system of equations. Since the EMF is equal to both of these things, I can just set them equal to each other. So basically 1 times 6 plus little r equals 1.5 times 3 plus little r. And we can solve for what little r is. Okay, so 6 plus little r equals 4.5 plus 1.5 little r, or 1.5 equals 1/2 little r. Therefore, little r is 3 ohms. So the internal resistance is 3 ohms. And we then need to find the EMF. So the EMF then would be, well, I could go back to one of these equations, like this top one right here, and I could put 3 ohms here. So 3 plus 6 is 9, and 1 times 9 is 9. So we get 9 volts of EMF. So that's a very common voltage for a cell. You can buy 9-volt batteries or 9-volt cells, and then this would be the internal resistance of that cell. So there you go. There's the background for activity 30. I hope that's helpful. Have fun with activity 30.